everyone, welcome to Science Friday.
Here's some for E as well. The one on the top here is one of the ways that you can define E.
What makes a field more likely to have an unbalanced gender distribution?
So this can be, like, in the case of this paper, gyrification or brain folds.
This goes back to balancing information retention.
Incredibly negative.
We have to emphasize privacy.
Doing today? Good? Awesome. So I've been thinking about this recently, and probably for most of you who know me, you already know this. I love talking. And something that I realized as I think about this more is that not only do I love talking, that's not really the main impetus of it. What I really like is talking when it works. I have this fear that one day I'm just going to talk, and then suddenly stop being able to talk anymore. The fact that I can speak is something magical to me. The fact that I can say words and have ideas and it just comes out into my mouth, I don't know how that works. So how does that work? How is it that I can conquer this? Because I am, at this point, obsessed with this idea. That I can talk and form ideas right in my head and have them spoken out loud just by the magic of my brain speaking it. Right? This is compounded even by me as a second language speaker to English. Right? I had to learn this language, but somehow it integrated in my daily words, and I can think about ideas and then speak them in English without me having to process them. But I can try to break this down, right? If we must break talking down into some kind of general aegis, it's three things. I first think about an idea. Let's take, this lovely green triangle. Say that's my encoding of my idea. I will conceptualize this idea and form the words I want to say in my head. I want to say green triangle, right? Those words come into my head. And finally, I spew it out loud, and people hear the words. Maybe after some filtering, maybe I don't want to say the word green, maybe I want to say the word triangle, and then finally I just speak that out loud. Of these three steps, though, I am particularly interested in one of them, this one. The idea that ideas can convert into words in my head. It's somehow grammatically correct. Like, I'm not making an effort to speak correctly right now. But somehow these ideas that I conceptualize in my head can somehow come out of my brain grammatically correctly without much of my effort. It feels kind of magical, right? The idea that I can speak and have words come out. No effort on my part. No effort in me trying to tell anything. But it just comes out. It just works. But no, obviously this is not magical. The idea of converting an idea like a green triangle into words, this is called language modeling. This is something that every single one of us do. We all are language modelers. We all are able to do this. It's the process of converting a concept or idea into words. Now, when we're engaging in normal conversation, we aren't just language modelers. We are conversational language modelers. We model words into other words. We compare ideas by bouncing them around and essentially converting some words into some other words. Now, this is not a process that is intrinsic to humans. People, especially recently, have been able to replicate this using statistics. The process by which conversational language modeling could be done by non-human things is by using something called language models. And language models are a statistical model, a model of probability, predicting the conversion of some words into other words so that they make coherent sense next to each other. Y'all with me so far? Awesome. So first, turn to your partner. Let's talk a little bit about this. What are some uses of language models that you can see in your daily life that has this ability to get a set of words and turn them into other ones? Awesome. Wrapping up, any last minute thoughts? And coming back together. Wrapping up, any last minute thoughts? Coming back together. So the idea of language modeling, what are some thoughts we have? What are some uses for these models?
Maybe say something like, I'm hungry. Somebody else responds, want to get lunch?
Exactly.
Converting hungry to lunch. Jack, could you repeat what's being said?
So Brock's proposal is, for instance, we can have a system that would, if I say I'm hungry, well, you respond with, can we get lunch, right? It's a system that predicts, it's associating hunger with food, right? Anything else?
An example of a more automated one in the real world that doesn't always work as well as it could is like the Gmail auto response feature.
Yeah, so another language model we can use is take an email, for instance, a context from an email, and then responding it with something, right? Predicting automatic responses. Anyone else? So language models, as we can see, have a variety of uses. It does any part of this. I'm going to introduce a not super new language model today, but one that's effective and has dramatically changed the industry of language modeling. And it all starts with this guy. I am losing my screen. Ours starts with this guy, which is Ashish Vaswani. He is a research scientist at Google. Now, 4 years ago, he came up with this paper called Attention is All You Need. And that revolutionized the language modeling or the natural language processing and computer language industry because of the fact that it's able to generate really, really high quality languages. This is what it's called, the transformer. Nope, wrong picture. Nope, still wrong picture. There it is. Aha. So the transformer. This transformer is a super, super good language model. It's able to replicate high quality utterances, real human sounding utterances between any two pairs of sentences. And to give you like a really brief overview, it kind of works like this. There's two blocks, what we call an encoder and what we call a decoder. And let's simplify this a little bit like this. So a transformer is what we call an encoder-decoder architecture, which means it takes a single sentence, it will pass it into one of the two computer language models, statistical models, and you end up with what's called an intermediate representation. Now, you can think about this as kind of like a green triangle, right? This is what our language model, the encoder part, thinks is the idea that it's trying to understand. So, can you explain, all of you, to your neighbor what the numbers on the top mean?
No.
All right. So, thanks, Steve. So, OK, let's try this again. So basically, if we take a sentence, we pass it to the encoder network. It's kind of like the understanding that this model has to the initial sentence. The model's building an understanding of our input sentence. And that's kind of like the analogy I had before, which is that of the green triangle. It's sort of the idea that the model's trying to communicate that it predicted from the input sentence. We're not talking about the output yet. It's just the input. So now, can you try to turn to your neighbor and talk about what the green triangle means? Sorry, the numbers on the top mean. Wrapping up, any last minute thoughts? Coming back together. Wrapping up, any last minute thoughts and coming back together. So, when we have intermediate representation, which is the idea of this, which is what the model understands, what the question is asking, is essentially a series of numbers representing the model's understanding what the input sentence means. We're not even getting to the generating and output part. But then, guess what's happening? We take this intermediate representation, we pass it into yet another network, and you end up with the output sentence, what the model wants to say. So that's the output sentence. This is what happens when you're using the model. You take a sentence as input, you pass it to the model, you get an intermediate representation, the model makes a decision on it, it gets an output. When you're trying to make this model better, when you're trying to make this model more efficient or make this model do what you want to do, you'll need both the input and output. You feed them both into the model, and the model becomes better. This pair of things, the input and its matching output, is called a sentence pair. I know, crazy imaginary naming. It's great. And if you take a sentence pair, and you have a lot of them, you end up with what's called a sentence corpus. It's quite a lot of sentence pairs. And when you're training a transformer, I know, shocking, right? When you're training a language transformer, you'll actually need quite a lot of these sentence pairs, like 100,000. So that's a lot. And not only do you need quite a lot of sentence pairs, you need a lot of sentence pairs that model the problem you're trying to model. Now model what you're trying to get out of your language model. What specific thing that you want to do. So what do we want to do again? That's right. We're trying to train a model that would be able to mimic the process of psychotherapy. Now, only the linguist parts. There's like a huge amount of psychotherapy parts that are not on the linguistic side. We're exclusively worried right now, about the linguistics part of psychotherapy. So it's just the text and response. So here's a problem with psychotherapy, though. Psychotherapeutic data of people talking to each other are especially hard to come by. And not only because it's something that you shouldn't probably be recording in an actual clinical setting, there are laws preventing you from really being able to capture most of these conversations. But here's a brilliant thing. In 2018, as an exercise for Stanford, the Department of Physics of all things, decided to look around, trying to look at a similar problem. How do we capture high-quality psychotherapy conversations that at the same time are not going to A, prevent breach patient privacy, and B, still be high-quality psychotherapy conversations? And you came across this website called Counselor Chat, who has a data set, which basically the way that this website works is that individuals would ask questions fully anonymously, professional psychotherapists would provide short responses, and there's a data set that they specifically build for their internal metrics that does use the standard state-of-the-art patient information protection systems to fully anonymize the data. And what's great about this data set is that A, it's not protected under any medical laws, but still it is anonymous, professional, that's the important thing, and open to any researchers. So we take the Counselor Chat data set, and that's about 2,000 samples. So if I did my math right, I think we still have like a little bit left, right? So talk to your neighbor. What should we do at this point, right? Should we find more data? It's really hard to come by. What are some thoughts? If you're trying to build a robot that can talk, but specifically talk about psychotherapy, what should we be doing? Just these sentence pairs. Where do we find lots of sentence pairs? So what are some thoughts that people have? Go ahead.
I mean, at least for starters, you can with the 2,000 samples to train it, and then maybe start with some more data.
Right. So you can start training by a very limited sample, right? That's one method.
Can you take the sample, like a small sample data, and like vary it in little ways to make it like more pseudo data?
Yeah, performing data augmentation, which is basically taking your existing data and just adding small tweaks so that it's the same data, but just you have more of it. Yep, that's one very valid way of doing it. Anything else? Go ahead.
I mean, you could find another data set that doesn't meet all your criteria, like conversations that aren't about psychotherapy, but are just between ordinary people and ordinary topics.
Aha! Thank you, Mark. What a perfect segue. Turns out the specialization data set, which is our 2,000 samples, doesn't actually have to be all of your data. There could be a base data set that does not have to be specialized. It turns out if you're building a model that can talk and act as a linguistics part of a psychologist, you first of all have to get the linguistics part, the part where it talks. And that doesn't actually have to be specialized. So where's some place where we can find lots of people talking to each other transcribed in text?
Hack Discord.
Huh?
Hack Discord.
Whoa, illegal word.
I guess that's one way. Anything else?
Like just large-scale chat forums in general that are open to anyone.
Exactly, long-form chat forums.
The internet
Movie scripts. Yes. Oh my God, people are really good at segueing. So, turns out there is this wonderful thing called movies from the 90s. Spot which ones you know. Turns out all of these are like basically on the internet, and it's not me who figured this out. Isaac Cornell did. They made what's called a Cornell movie dialogue corpus, which is a corpus of isolated conversations between two characters, pairwise matched up, that create natural conversations that, of course, writers wrote, but it's online and available. So, combining those things together, we end up with our sentence corpus. So, I proceeded to chunk them up, split it into training and validation, fed it into the model, and it became better. It didn't grow muscles, but close proxy. So here's a usage example. Here's a conversation. It's part of the input data set. So this was actually part of the input sentences that was fed in part of the data. But the output, we want to see how the model does. So we feed this input into the model. Boom, another set of numbers. And feed it back to the decoder, and we get an output. If we take all of this, chunk it together, here's how the conversation goes. This, just so you know, the user data sets, these are part of the data. And then the output is the model's desired output. So yeah, it's fine. But how good is this? Do you know? I don't know. Like, how do you figure out how good a conversation is? Fortunately, machine learning already has an answer for you. It's called validation metrics. It's the systems by which a model who does arbitrary things could be validated for its performance. And very recently, a company in San Francisco proposed a way of validating chatbot-specific methods that essentially is like a very, very advanced Turing test. And it's called a response quality index. It's a way of measuring the quality of a chatbot proposed very recently. And it's shockingly simple. Take 3 numbers, human graded, clarity, specificity, contribution. There are rubrics on this. I'll show you in a second. Multiply them together, and that's your RQI for any arbitrary sentence, a pair of sentences. These are the objectives of the scores, which is how clear was the response. Doesn't have to make sense, doesn't have to be relevant. It just has to be clear, like it was communicated. How relevant and specific was the response, meaning was it broad strokes, was it general, like 2 words that does make sense but mean nothing, or was it specific? And lastly, contribution, which is for the problem specifically you're solving, did it positively influence the user's query? So the way that the actual measurement was set up was we took a bunch of sentences, pairwise swapped them, 50% training data, 50% generated data. Basically, every other sentence is swapped. Sorry, half of every other sentence is swapped with the output from the model. We gave this to, I think, 137 people. And we ended up with these lovely results. And the beauty about this is that you can see, because every other sentence is swapped, we can correlate the responses that the grader scored for human responses and the responses the grader scored for bot responses. Does that make sense so far? This will be very important when we get to the actual numbers. So yeah, so the higher the number, the better. And yeah, go ahead.
Can you explain the interleaving part again?
Sorry?
The interleaving
So this is part of the withheld training data. So parts of the data that we did not include in the actual training process. We swapped out, so given the context from way before of the actual data, we swapped out every other sentence and predicted the next sentence to the actual result. So basically have the model predict every half of the sentence. Now, will the conversation fall out? Yes. And we're not testing for that because we're testing for the model-specific response with respect to all human written context and the sentence it's trying to generate. Does that make sense? Awesome.
Wait, so why are the users evaluating the human part? Shouldn't they be evaluating the bot's performance?
The only way that we can really evaluate a bot's model with human validation is also to validate human responses, the actual responses, so I have a baseline onto which we compare. And you'll see in a second that all my numbers that I report is actually how much the model did better than a human, and not really the actual numbers themselves. Because that's really what we care about.
Okay.
Anything else? We're kind of running out of time, but we're pretty close to being done. So there's two numbers. When human RQI is bigger than bot RQI, humans did better. But human RQI is smaller than or equal to bot RQI, when model did better. Here they are. Now, if you look at these numbers, they're not super exciting. Right? 40% of the time, the humans scored higher than the bot. And slightly higher did the bot score the same, and most of it was the same or slightly better than human responses. But, sorry, go ahead. The model could be better than humans, surprisingly, is because sometimes the model gave a port of scoring, averaged out, a more specific or relevant response. Because sometimes the humans may give a less specific or more general response that was scored slightly lower. And they only happen in like very few samples as well.
Why do we agree that specificity is a good thing? If they said, how do I quit smoking? And a human said, well, here's a couple strategies you could use. And your model said, this is the strategy you need to use exactly. Here's how I fine-tuned it to you. They haven't actually fine-tuned it to them, but they're a whole lot more specific. That doesn't actually sound to me like the model is doing better.
So this conversation metric is more about, the specificity aspect is not about the specific answer, is a linguistic specificity. So basically, is it answering in broad strokes or is it answering in specifics?
You're saying if they were more eloquent and used like more specific adjectives the way your English teachers want you to?
Not necessarily. Eloquence is not the score, though. What we're scoring for is the exact, not the number of words used, but the precision of the words used. But I also want to move ahead just because we're kind of running out of time. Okay. So we can talk about this later. But basically, if we split this up, it turns out that the humans did significantly better, like one standard deviation as well. It's only 7.2% of the samples. So the model is actually doing fine-ish for most of the results, sorry, for a part of the results and most of the other results. So it brings us to the broad strokes questions. Why do I bother? Like, why go through all of this effort to do this? And here's a few things. So remember that this model is not replacing the word of psychologists. It can't. It's only text-based. But at the same time, there are chat lines and hotlines who doesn't have the same amount of load that's required of actual trained psychologists such that they can answer questions and queries immediately. So this would be a very first good step to widen access, like a foot in the door type of thing, to do a little bit of triage. It will destigmatize because it's literally available anywhere, and no human have ever need to touch the data, and expedite the process of triaging someone who really need to get to someone that that is trained to be able to resolve their query. And remember, this is not therapy. This is not the process that really helps people through. It's only the intro to getting them help. And the process, the way that to handle and deload the sort of the entry level part to be able to bring them into a broader scope in the field. And also remember, essentially 2.2%. If a parachute jump, if you're a parachutist, is that the word? And the parachute didn't work 7.2% of the time, would you trust it? No. This is a life and death issue, and this is something that a model to this day still cannot handle. And it's nevertheless a proof of concept for the idea of training models on very limited data and being able to get coherent responses. So don't try this at home, folks. Thank you.